Number 1 says you read in a book on poker that the probability of being dealt 3 of a kind in a 5-card poker hand is 1 out of 50. What does this mean? So even if you don't know poker, you still should be able to answer this question. It's just assessing you on your basic understanding of probability. So the correct answer is A. If you deal thousands of poker hands, the fraction of them that contain 3 of a kind will be very close to 1 out of 50. So this has to deal with the fact that probability is long-term relative frequency. Okay, and this whole idea of just because something there's a chance of 1 out of 50, that doesn't mean, for instance, letter B says if you deal 50 poker hands, one of them will contain 3 of a kind. That's not true because probability in the short term is unpredictable, but in the long term you can estimate the probability of things. It's kind of the same idea if I were to flip a coin. Just because the probability of heads is 1/2 or 1 out of 2, that doesn't mean if I flip a coin twice, exactly one time it'll be heads. It means if I flip a coin thousands of times, approximately half of the time it would be heads. Okay, number 2 says if a peanut M&M is chosen at random, the chances of it being a particular color are shown in the table below. So it says the probability of randomly choosing a blue M&M, so that's this right here. Well, we have to use a rule that the sum of the probabilities in a sample space is equal to 1. So we can add 0.3 plus 0.1 plus 0.2 plus 0.2 plus 0.1, which is 0.9. And since they're supposed to add up to 1, we can just subtract from 1. So the probability of drawing a blue M&M is 0.1. Number 3 says Miss Okita only likes blue and orange peanut M&Ms. What is the probability that she chooses an M&M at random? She will choose one that she actually eats. So I'm really trying to find the probability that the M&M I choose is either blue or orange. So or means we add, so I'm just going to find the probability of blue plus the probability of orange. So the reason we don't have to subtract anything is because an M&M cannot be blue and orange at the same time, so there's no overlap. So for this, it's just going to be 0.1 plus orange, which is 0.1, so that's 0.2. So the probability I'm going to choose when I actually eat is 0.2. Number 4 says, what is the probability that a randomly chosen M&M is not green? So in probability, the word not means complement, which means we're just going to subtract from 1. So we're trying to find the probability that it's not green, or we can say green complement. So that's just going to be 1 minus the probability that it is green. So 0.2, that's 0.8. All right, number 5 says an athlete suspected of using steroids is given 2 tests that operate independently of each other. Test A has a probability 0.9 of being positive if steroids have been used, and test B has a probability of being positive if steroids have been used. What is the probability that neither test is positive if steroids have been used? Okay, so we know that the probability that A is positive is 0.9 if steroids have been used, and we know the probability if B is positive is 0.8. But we want to know the probability that A and B are both negative. So neither test is negative, so we need A and B to be negative. Well, first I need to find the probability that A is negative if steroids have been used. And if the probability that it's positive is 0.9, then that's just 1 minus 0.9, which is 0.1. And then we need to find the probability that B is negative. And that's just going to be 1 minus 0.8, which is 0.2. But I want to find the probability that both are negative. For that, we're just going to multiply 0.1 times 0.2. Oops, sorry. 0.1 times 0.2, which is 0.02. So the reason we multiply is because we want A to be negative and B to be negative, and since they're independent, we know that we don't need to worry about any conditional probability. So 0.02 would be the probability that both tests are negative if steroids have been used. All right, number 6 says an instant lottery game gives you probability of 0.02 of winning on any one play. Plays are independent of each other. If you play 3 times, the probability that you win none of your plays is about, so we're trying to find the probability that we lose all 3 of our plays. Well, the information they give us a probability of winning, which is 0.02. So now we need to find the probability of losing, which is just 1 minus 0.02, which is 0.98. And since we want to lose 3 times, we're trying to find the probability of losing 3 times. And since they're independent, that means the probability is the same on each play. That's just going to be 0.98 to the 3rd power, which works out to be about 0.94. So this is basically saying I'm going to lose on the first one, lose on the second one, and lose on the third one. So that's why it's raised to the 3rd power. And because they're independent, it means the probability is the same each time. All right. Number 7 says the probability that you win at least one of your plays of the game in the previous question. Well, remember that the probability of at least one is the same thing as 1 minus the probability of none. Well, we found this problem in the previous question, or we found this answer in the previous question. The probability that we lose all 3 plays we know is 0.98 to the 3rd power, because that would be lose, lose, lose. So to find the probability of at least one, we're just going to subtract it. So it's going to be 1 minus 0.94, which is 0.06. So this is a probability that we win at least one. All right, so number 8 says choose an American at random. The probability that you choose a woman is 0.52. The probability that the person you choose has never married is 0.24. The probability that you choose a woman who is never married is 0.11. The probability, and we're trying to find the probability that the person you choose is either a woman or never married. So we're trying to find probability of a woman or never married. So or means we're going to add. So we're going to find the probability that we choose a woman plus the probability that that woman is, or probability that someone is never married. But these are not disjoint because you can have a woman who is never married, so we need to subtract the overlap. So woman and never married. Well, in this case, we're given all of this information. So we have the probability of a woman, that's 0.52. We have the probability that the person you chose is never married. And we have the probability that you chose a woman who has never married. So that's a woman and never married. That would be this last one. So filling in what we know, it's going to be 0.52 plus 0.24 minus 0.11. And this represents the overlap. So this works out to be 0.65, which is B. All right, so number 9, it says which of the following is or are true. It says the sum of the probabilities in a probability distribution can be any number between 0 and 1. 2 says the probability of the union, which is or, of 2 events is the sum of the probabilities of those events. Number 3, it says the probability that an event happens is equal to 1 minus the probability does not happen. Okay, well in this one, I'm going to go through each one. So number 1 says the sum of the probabilities in a probability distribution can be any number between 0 and 1. So this is false because the sum of the probabilities always has to equal 1. Okay, looking at number 2, it says the probability of the union, so or of two events, is the sum of the probabilities of those events. So that one seems like it's right. However, remember we always have to consider the overlap. We have to consider the overlap. We have to subtract the overlap, just like in problem number 8. So the reason why 2 is false is because this is only true when the events are disjoint or mutually exclusive. So far we know we can cross off A and B, and we can cross out all of the above since we know A and B are false. So now we look at C. It says the probability that an event happens is equal to 1 minus the probability does not happen. That is true. That's basically the complement rule. So C is the only one that is true. All right, number 10 says an event A will occur with probability 0.7. Event B will occur with probability of 0.3. So the probability of A is 0.7. Probability of B is 0.3. And then we have the probability of A and B, which is 0.2. We're trying to find the conditional probability of A given B. So that's this. And using the formula we talked about, if we say A given B, that means the numerator is where A and B both happen. The denominator is the second thing, the given information. So now we just have to fill this in. Well, we have the probability of A and B, so that's going to go there. So that's 0.2. And then we have the probability of B. So that's going to go here. So it's going to be 0.2 over 0.3, which is about 0.67. All right, so now let's look at the free response. So it says we're rolling 2 standard fare dice. We're trying to find the probability of getting doubles. So doubles would be 1, 1, 2, 2, 3, 3, etc., etc. Well, the probability of rolling 1 and 1, since these are independent, the probability is the same. So that's 1/6 squared, which is basically 1 out of 36. So if I want to find the probability of rolling any doubles, we know that there's 6 different ways, right? Because we can roll 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. So there's 6 different ways to roll doubles. So we're just going to multiply by 6. So 6 times 1 out of 36. You end up with approximately 0.17. All right, B says, what is the probability of getting an even sum? So what might be helpful here is drawing your table. Remember, when rolling 2 dice, we can roll a 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12. And remember, the number of ways starts at 1, goes all the way up to 6, and then goes back down to 1. So then to figure out the probability, the total number of ways is 36. So we know it's just going to be over 36. So if we want to get an even sum would be rolling a 2, 4, 6, 8, 10, or 12. So we're going to add together these number of ways. So it's going to be 1 plus 3 plus 5 plus 5 plus 3 plus 1. And remember, there are 36 total ways to roll 2 dice. So that's going to be 18 out of 36. So that's 0.5. All right, so now looking at C, we're trying to find the probability of getting at least a sum of 5. So at least 5 would be 5 or more. So the number of ways you can get a sum of at least 5, we would add together 4 plus 5 plus 6 plus 5 plus 4 plus 3, 2, and 1. So that's the number of ways you can get a sum of at least 5. And again, it's over 36 because there are 36 different ways we can roll 2 dice. So this is 30 over 36, which works out to be about 0.83. All right, D says a probability of getting a multiple of 3 or an odd number. Okay, so or means we can add. So we're going to do the probability of a multiple of 3 plus the probability of an odd. But then we need to subtract the overlap because there is overlap between multiples of 3 and odd numbers. So we're going to subtract multiple of 3 and odd. Okay, so first finding the multiple of 3, that's going to be 3, 6, 9, and 12. So that's 2 plus 5 plus 4 plus 1 over 36. So the number of ways to roll a 3 is 2. The number of ways to roll a 6 is 5. The number of ways to roll a 9 is 4. The number of ways to roll a 12 is 1. And then we're going to do the probability of odd. So odd is going to be 3, 5, 7, 9, and 11. So that's going to be 2 plus 4 plus 6 plus 4 plus 2, again over 36. And then we need to subtract the overlap. So any numbers that are both multiples of 3 and odd. So that would be 3, and that would be 9. So those are the ones that are multiples of 3 and odd. So that's going to be 2 and 4. So 2 plus 4 over 36. So this works out to be 24 over 36, which is approximately 0.67. So this first one represents the probability of getting a multiple of 3. The second one represents the probability of getting an odd number. This third one represents a probability of getting a multiple 3 that is odd, which is only 3 and 9. All right, so looking at number 12, we want to know, okay, we're flipping a coin 4 times. We want to find the probability of exactly 3 heads. Well, we could make a tree diagram for this, but that will most likely be a little bit confusing. We can kind of just think through, if we're flipping a coin 4 times, to get 3 heads, let's see, we can get heads, 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 tails. We can get heads, heads, tails, heads. We can get heads, tails, heads, heads. Or we can get tails, heads, heads, heads. These are the only ways that you can get exactly 3 heads. So then we need to figure out how many things in my sample space. Well, if there's 2 ways you can get, or 2 things you can get on the first toss, 2 things you can get on the second, 2 on the third, 2 on the fourth, we can use a multiplication rule and do 2 times 2 times 2 times 2. There are 16 ways to flip a coin 4 times. And if there are 4 ways to get exactly 3 heads, that means the probability of exactly 4 heads is just going to be 4 out of 16, which is 0.25. All right, B says, what is the probability of at least 1 heads? So the probability of at least 1 head is equal to 1 minus probability of no heads. Well, we know the probability of no heads is 1/2, because that's basically tails, but we want no heads in 4 tosses since we're flipping a coin 4 times, which means that's just going to be 1/2 to the fourth power, because we want no heads and no heads and no heads and no heads. So to find the probability of at least one, it's just going to be 1 minus 1/2 to the fourth power, which is 0.9375. All right, number 13 says we are going to select 5 cards from a standard deck of 52 without replacement. What is the probability of selecting at least one ace? So again, this is an at least one problem. So the probability of at least one ace is 1 minus the probability of no aces. And we are picking 5 cards, so no aces in 5 draws. Remember, with at least one problems, we're going to find this probability. So the probability of ace, we know, is 4 out of 52, which means the probability of no ace is 48 out of 52. But that's in one draw. But since we're drawing 5 cards, that means the probability of no ace in 5 draws. Since we are not replacing it, that means our sample space, the probability changes on each draw. So on the first draw, it's 48 out of 52. On the second draw, it's 47 out of 52. Or sorry, 47 out of 51. And then 46 out of 50. 45 out of 49. And then 44 out of 48. So this represents the fact that we are not replacing the card. So the amount of cards that are not aces decreases, and the amount of cards in our total sample space also decreases. So this, when we put this in our calculator, works out to be about 0.659. So that means, and that represents this part right here. So to find the probability of at least one ace in 5 draws is just going to be 1 minus 0.659. Which is 0.341. All right, looking at number 14. So number 14 says the following data represents the number of traffic fatalities in the United States in 2005 by person type for male and female drivers. So the first thing we need to do is we need to get our row and column totals. So the total for male is going to be 25,987, just adding these two together. The total for female is going to be 11,494. The total for drivers, so now we're adding across, it's going to be 27,395. And the total for passengers would be 10,086. And the total is 37,481. All right, so now it says choose a fatality at random. What is the probability that the victim is male? So we have a total of 25,987 males out of a total of 37,481. So that would be the probability that it's a male. That works out to be about 0.69. B says the conditional probability that the victim was male given that the victim was a driver. So we're trying to find the probability of it male, being a male, given that he was a driver. So that means our numerator is going to be the probability of, it's going to be male and driver. And then the bottom is we know that they're drivers. So we're only looking at the drivers. So the denominator is the total number of driver fatalities, which is 27,395. The numerator is in that column. So in this column, because we're only looking at drivers, how many were male? And that's going to be the 20,000 number. So 20,797. So the top represents the total male driver victims. The denominator represents the total number of drivers, or total number of fatalities that were the driver. So this is about 0.76. Okay, C looks the same as B, but it's different. It's the conditional probability that the victim was a driver given that the victim was male. So in this one, the information we know is different. We know that the driver was male, which means we are only looking at this column. So the total number of males is 25,987. And in that column, the total number of fatalities that were drivers is 20,797. So the only thing that changes between problem B and C, the denominator is the one that changes. The numerator stays the same because the numerator, we're looking for people who were males and the drivers. The denominator changes because the given information changes. So this works out to be 0.80. All right, so the last problem is conditional probability again, but these ones, it's a table with probabilities, but that doesn't change the way we do them. We still get our row and column totals. So I'm going to get the column totals first. So the first one is 0.25, and then we have 0.35, we have 0.22, and 0.18. And then the column totals, or sorry, the row totals, we have 0.61, 0.24, and 0.15. Remember, with a table of probabilities, we don't need to divide by anything because these are already probabilities. The total, when you add these all together, so when you add these three numbers together, it is going to equal 1. Okay, so looking at A, it says, what is the probability that the individual does not have health insurance? So no health insurance, we're just looking at this bottom column. So it's just going to be all of these added together. So it's 0.03 plus 0.08 plus 0.03 plus 0.01, which is 0.15, or we can just look at our column total or row total there. B says, what is the conditional probability that the individual has government health insurance given that the individual is at least 65 years old? So we're trying to find the probability of government health insurance given that they're at least 64 years old. So using the conditional probability formula, that's a probability that they get government health insurance and they're at least 64 over the probability that they're at least 64. So we're only looking at this column. So the probability that they are at least 64 is 0.18, so that's my denominator. And in that row, the total proportion that have government health insurance is 0.10. So it's 0.10 over 0.18, which is 0.56. C says, what is the probability that the individual has either private health insurance or at least 65 years old? So for this one, or means we're adding, so we're trying to find the probability. It's private health insurance, so private health insurance plus the probability at least 64. But then we have to subtract the overlap, probability that it's private health insurance and at least 64. So the proportion that has private health insurance is 0.61. The proportion that is at least 64 is 0.18. But we are double counting where they overlap. The people who have private health insurance and are at least 64, which is 0.07. So this represents the overlap. So this total is going to be 0.72.